Okay, we saw from Raoult's law that the vapor pressure of a solution is lower than the vapor pressure of the pure solvent, so that means the boiling point will have to go up. We'll have to go to a higher temperature to hit the normal boiling point for the solution, since the vapor pressure has been lowered. It takes a higher temperature to get to 1 atmosphere pressure for vapor pressure. We can quantify this by saying that the change in the boiling point is equal to a constant, which we call the boiling point constant, times the molality of the solution. So now we need to define what molality is. So molality is given the symbol little m, whereas molarity is given the symbol capital M. And you remember that the molarity is equal to the moles of the solute over the volume of the entire solution. However, the molality is equal to the moles of the solute divided by the mass of the solvent in kilograms. So this is molality, moles of solute divided by kilograms of the solvent. So delta T boiling point, and this is the elevation in boiling point, is equal to a constant. So this constant is different for each solvent, and then we multiply by the molality of the solution. So let's do an example. So say we have 100 grams of sugar and 250 milliliters of water. What is the boiling point of the solution? So we would need to know the molality of the solution, and we look up K, the boiling point constant for water, in a table. So delta T boiling point is equal to K, the boiling point constant for water, because water is our solvent. So that's 0.512 degrees centigrade per molal. And then we multiply by the molality of the solution, which is the moles of the solute So this is the moles of the solute, its mass, 100 grams of sugar, divided by its molecular weight, 342 grams per mole. Then we divide by kilograms of solvent for molality. So water is 1 gram per milliliter density, so this would be 0.250 kilograms of water. So remember, this mass is in kilograms for molality. So this is the molality of the solution. So this would give us a change in boiling point of 0.6 degrees centigrade. So that means the boiling point of our sugar solution would be 100.6 degrees centigrade. So the boiling point would go up by about ½ a degree. Okay, now let's look at freezing point lowering, and this has the exact same form. So the change in the freezing point of a solution is equal to its freezing point constant times the molality of the solution. So we would look up the freezing point constant for our solvent and then calculate the molality of the solution. That will give us our change in freezing point. So let's do the same example. We have 100 grams of sugar and 250 milliliters of water. And we want to know what the freezing point of our solution is. So delta T freezing point, this is the change in the freezing point, is going to be equal to the freezing point constant for water, which is 1.86 degrees centigrade per molal. And then we multiply by the molality of the solution. So that's moles of solute. So that's 100 grams of sugar times 1 mole per 342 grams of sugar divided by the kilograms of solvent. So that's 0.250 kilograms of solvent. So this gives a freezing point depression of 2.2 degrees centigrade. So remember, this delta T is the lowering of the freezing point. So my freezing point will be negative 2.2 degrees centigrade because this delta T is a freezing point lowering. So what if we have a solute that dissociates upon dissolution, say sodium chloride? So we take one sodium chloride molecule, dissolve it in water, and it dissociates into two separate ions, a sodium plus and a chlorine minus ion. So if we have 0.1 moles of sodium chloride in 250 milliliters of water, when we dissolve sodium chloride, we'll have 0.2 moles of solute in 250 milliliters of water. Because we start with one thing, we end up with two things when sodium chloride dissolves. So we have to take into account the number of solute particles. Their identity doesn't matter for colligative properties, only the number of solute particles. So if I reference molarity of sodium chloride, I have to double that for the dissociated ions. And so one way we can keep track of this is for the boiling point and freezing point, is to multiply by this factor called the Van Hoff factor. And this is the dissociation factor. So for sodium chloride, one particle dissociates into two particles, so I would be 2. If we had, say, magnesium chloride, we have one particle dissociating into 3 separate ions. 1 magnesium 2 plus and 2 chloride ions. So we have a 1 to 3 ratio. And so the Van Hoff factor would be 3 for magnesium chloride. So again, it doesn't matter the identity, just the number of solute particles. So we'll do an example. So say we take 100 grams of sodium chloride and dissolve it in 250 milliliters of water, and we want to know what the freezing point of the solution is. So we have our freezing point depression is equal to, since this is an ionic compound, we'll use the Van Hoff factor. And so I will be 2 because sodium chloride breaks up into 2 separate ions. So this will be 2 times the freezing point constant times the molality of the solution. And the molality of the solution is 100 grams of sodium chloride. That's 58.4 grams per mole is the molecular weight. This is the molality of the solution. So this is the moles of sodium chloride divided by kilograms of solvent. So we have 250 milliliters of water, so that's 0.25 kilograms. So the molality is equal to 6.9 molal. So we'll substitute that in for the molality. And our freezing point depression will be 25 degrees centigrade. So this is the freezing point depression. So the freezing point of my solution will be negative 25 degrees centigrade for this very concentrated salt solution.